This is the video for the online final exam practice test that covers the periodic table and trends portion. This first question, it says, which of these is an alkali metal? So if we look back at our periodic table, the groups on the periodic table, the first column, excluding hydrogen because that is a gas, are the alkali metals. These are the most reactive metals generally. Then the second column is the alkaline earth metals. You have the transition metals in this center section, the D block. You have the halogens, which are fluorine on down. And then you have the noble gases, which are pretty stable elements. The rare earth elements, you have the lanthanides that begin with lanthanum and that row that follows it. And then you have the actinides that begin with actinium. So if it was asking alkali metals, it's any of the elements from this first column excluding hydrogen. Right, so in this case, that would be cesium. How many valence electrons do most of the noble gases have? All right, remember, valence electrons end up being pretty straightforward. You just count left to right, ignoring the transition metals. So 1, 2, 3, 4, 5, 6, 7, 8. So it says most of the noble gases because helium is the one exception. It is a noble gas, but it only has 2 valence electrons because it's a 1s energy level, so that can only hold at most 2 electrons in that orbital. But it is lumped in with the noble gases because its valence shell is full of electrons, so it tends to be relatively stable. It doesn't really react with much, so it is considered a noble gas, but that's why it says most there. The most chemically reactive nonmetals. All right, if it's asking nonmetals, it's everything to the right of this step ladder here, because the metals are to the left. The metalloids are the ones that fall on this ladder, except for aluminum. If you test that, that is purely metallic. And the nonmetals are everything to the right. So if it's asking the most reactive, chemically reactive nonmetals, what you're looking at are the halogens. They only have to gain 1 electron to get a noble gas electron configuration, and they can do that very quickly. So things like fluorine, chlorine, bromine, iodine, they will be very reactive. Same thing with the alkali metals. They are also very reactive because they only have to lose 1 electron to become like a noble gas, to get that full outer shell electron configuration. All right, so something like lithium, sodium, potassium, rubidium, cesium, francium, they give away 1 electron, they become like the noble gases. All right, but this one was asking nonmetals, so that would be the halogens. The alkaline earth metals, now it's asking oxidation number. Oxidation number generally goes +1 above the alkali metals, +2 above the alkaline earth metals. We can write these in. And so you have +1, +2, +3. A lot of times people put plus or -4 here. -3, -2, -1, and we tend not to put anything above the noble gases because they are, for the most part, unreactive, mostly unreactive. The way we get the oxidation numbers is the charge that you get after these elements gain or lose electrons. So the alkali metals tend to lose 1 electron to be like a noble gas, to get that noble gas electron configuration. So when you lose an electron, you end up with a +1 charge. The alkaline earth metals, which is what this question was asking, end up with a +2 charge. They have to lose 2 electrons. And this is why they tend not to be quite as reactive as the alkali metals. It is more difficult, it takes more time to lose 2 electrons, so they're not as reactive. Same thing with the halogens. This is why they're so reactive. They only have to gain 1, where the oxygen group has to gain 2. So this is the general idea for oxidation numbers. Just remember the transition metals, that a lot of those are considered multivalent, and that's what the little numbers in the upper right-hand corner mean. They're always positive because they're metals. So copper, for example, can be a +2 or a +1. Now, some of them only have 1 oxidation number. So zinc, for example, can only be +2. All right, so that's oxidation numbers. So oxidation number of chlorine, that was a halogen, so that was in the -1 column there. The smallest atomic radius, so we're going to go back to the periodic table and look at some trends here. So when you're looking at trends on the periodic table, the ones that come up on this review are atomic radius and ionization energy, but there were a couple other ones. So it happens as you move down a column on the periodic table, the atomic radius increases. And what's going on there is you're adding more and more energy levels, so it's just getting bigger and bigger. Now the ionization energy does the exact opposite. That decreases. Ionization energy is how much energy it takes to remove an electron. So the bigger the element, the farther the electron is from the nucleus, right? Remember, the electrons are negatively charged, the protons are positively charged, so there's some attraction there. But if the electrons are farther away, it's going to be easier to take them away from the nucleus. Now, as you go left to right, those trends switch. Atomic radius decreases, ionization energy increases. The atom is getting smaller as you go left to right, so it's easier to take those electrons away. Now, other trends we talked about were electron affinity and electronegativity, and they follow the same trend as ionization energy. And the other thing we talked about was shielding effect. That is the blocking of the inner electrons, making it basically more difficult for the nucleus to hold on to the outermost electrons when you have a lot more inner electrons. So when you consider these two atoms, there's not many inner electrons here. So those protons would have a pretty good hold on those electrons in the outermost energy level, the valence electrons. Where in this one you have more electrons between the protons and the outermost electron. So those protons can't hold on to that outermost electron quite as well. All right, so shielding effect is the only one that we were saying doesn't change as you go left to right. So if we keep that there, we can go back and see what our options are here for the questions. All right, so smallest atomic radius. The options are strontium, magnesium, beryllium, and calcium. Let's go back then. So we can figure out what we have here. So we're looking at strontium, magnesium, beryllium, and calcium. All right, so we're in a column here, so this one's pretty straightforward. Atomic radius increases as you go down, so if you're talking about the smallest atomic radius, it's going to be the one that's highest up. Now, the next question is saying which of the following elements has the smallest atomic radius, and the options now are beryllium, neon, nitrogen, oxygen, and carbon. So now you're going left to right. They're all in the same row or period, and it's asking smallest atomic radius, and the atomic radius gets smaller as you go right. So in that case, it would be neon. It's just farthest to the right. Take these out so it doesn't confuse us for the next problem. All right, which is larger? It says calcium or calcium with a +2 charge, and it wants to know which of these two is larger. Now, calcium, if it's neutral, has 20 protons and 20 electrons. For a +2 charge, the protons don't change, but it lost 2 electrons. So now what you have is 20 protons holding on to only 18 electrons. So you can think about the protons as having a stronger effective nuclear charge relative to the electrons. Those 20 protons are able to pull on those electrons more, causing that cation to shrink. So if it's asking which is larger, it is the neutral element. Now, if you're talking about negatively charged ions, so say you have, I don't know, something like bromine, and bromine with a -1 charge, the bromine with a -1 charge would be the bigger of the two. because it goes from having 35 protons and 35 electrons to 35 protons and 36 electrons. So in that case, the 35 protons would not be able to hold on to the 36 electrons as well, and they're able to spread out away from the nucleus a little bit. They're able to migrate out. All right, the next question, the largest ionization energy, and the options were rubidium, potassium, sodium, cesium, and lithium. Ionization energy is how much energy it takes to remove an electron. So the largest ionization energy would be the smallest atom, because this is where the electrons are closest out of this series, closest to the protons, that are able to hold on to them the most. So that would be lithium in that example. Ionization energy decreases as you go down. The atom is getting bigger, so the valence electrons are easier to take away, which is why something like cesium would be more reactive than some of those other elements that are above it. The largest ionization energy. All right, so now we're looking at nitrogen, fluorine, lithium, oxygen, carbon, and beryllium. Now it wants to know the largest ionization energy. And when I think high ionization energy, you should be thinking the nonmetals. The nonmetals tend to gain electrons, so they're not really going to lose electrons very easily. So what we get here is fluorine is the smallest out of the options here, because atomic radius decreases as you go left to right. So fluorine is going to be the smallest of those atoms. The electrons are going to be closest to the protons in the nucleus, so that's going to have the highest ionization energy out of that group. It ends up being very difficult to take an electron away from fluorine, like I said, because it really has a tendency to gain one to be like neon. So it's going to be really hard to lose one and go the opposite direction. All right, so that is the review for the periodic table and trends section of those online review practice tests.